This lecture is the first of 2 lectures in which we will review the topic of microwave impedance matching networks. The specific objectives of this lecture are to review the reasons why matching is needed, to discuss the limitations of matching networks and the Bode-Fano limit. Let's begin by remarking about the importance of impedance matching. One reason why we might want to do impedance matching is to ensure maximum power transfer. On the transmit side, we need to ensure maximum efficiency, basically maximum effective isotropic radiated power relative to prime power, battery power, or power we're getting from the AC grid. On the receive side, we want to minimize the noise figure and decrease the minimum detectable signal. The lower is the minimum detectable signal, the more sensitive is your receiver. Another reason for doing impedance matching is to eliminate the effects of multiple reflections. Multiple reflections can manifest themselves as intersymbol interference in digital systems. And yet another reason why impedance matching is important is because we want to minimize amplitude and phase errors in a power distribution network. For example, for a phased array antenna, in order to maintain low side lobes in a radar application, for example. This picture shows a generator with characteristic impedance Z0 connected to a load of impedance ZL, and in between the generator and the load is a matching network. And what we would like to have at the input to the matching network is an impedance equal to Z0, so that we are delivering maximum power from the generator to the load. And of course, this is assuming Z0 is a real quantity. If it were complex, then Zn should be equal to Z0 conjugate. But almost always the system impedance Z0 is a real quantity. Now this is a important concept to grasp. If I have a lossless matching network, then maximum power transfer is satisfied at every point in the matching network. So here I'm showing a generator with an internal impedance of Z0, which is real, connected to a matching network to a load ZL. Now, if I look into the input terminals of the matching network, I see Z0 in the ideal situation. If I look into the output terminals of the matching network, then I should see ZL conjugate. But if I slice into anywhere in the matching network, and I look to the left and I see Z left, and I look to the right and I see Z right, then the maximum power transfer relationship does need to be satisfied. So we must have that Z left is equal to Z right conjugate. And again, this has to hold at every point in the matching network. Now, it turns out that we don't generally want to design a matching network to work at a single frequency. We'd like it to work over some bandwidth. And the bandwidth of a matching network can be defined as the range of frequencies over which the input reflection coefficient is less than some maximum acceptable reflection coefficient magnitude. And we could also express this equivalently, completely equivalently, in terms of return loss or standing wave ratio. As long as the real part of the load is positive, greater than 0, a perfect match can be obtained, at least in theory, at a given frequency point. Now, there's some good reasons why you may not be able to achieve it, because if RL is very small, compared to the reactive part, it may be very difficult to achieve the perfect match in the face of component tolerances, etc. The frequency bandwidth over which an acceptable match can be obtained depends on the Q of the load. If the Q is too high, then 1, it may be impossible to match the load over enough of a frequency range to be useful, and or 2, the match is so sensitive to component and dimensional tolerances as to be virtually worthless, because you could never achieve the match because any small change in your component value or dimension is going to make it not work. Another concept that's important to understand in impedance matching is that we always want to use purely reactive components in the matching network. Otherwise, we will have an intentional reduction of efficiency, which is generally not desirable. Now, there is an exception to this. If your Q is very high, such as for an electrically small antenna, you may want to introduce some loss to DQ things, and this will make your matching network work over a broader frequency range and additionally make it less sensitive to component and dimensional tolerances. There are numerous factors affecting the selection of a particular matching network topology. Some of these factors are complexity, bandwidth, implementation, adjustability, cost, size, and sensitivity or repeatability. Now, matching networks can comprise either lumped or distributed components, or a combination of the two. For lumped components, there is generally an upper frequency limit imposed by the self-resonant frequency of the component. And for transformers or inductors, this is quite a bit lower than it is usually for capacitors. On the other hand, the lower frequency limit of a distributed transmission line component is its physical size. This picture shows some lumped components that might be used at microwave frequencies. These components have finite quality factor due to dissipative losses. They have finite self-resonant frequency due to parasitic effects. In this slide, I'll attempt to quantify the maximum frequencies for certain discrete lumped reactive components. For RF transformers, it's very hard to find ones that will work above the upper VHF range, say 200 to 300 megahertz. For RF inductors, 2 to 6 gigahertz is about the maximum. For RF capacitors, somewhere between 5 and 20 gigahertz, one will find that they are not really working too well. And we should note that we can still realize lumped capacitors and inductors at higher frequencies by using gaps and narrow sections of transmission line. Let's talk about choices for realizing lumped reactive components. One way to implement a lumped reactive component is by using off-chip discrete components. These things are sometimes called chip capacitors and chip or mini-spring inductors. The term chip here meaning ceramic chip, not silicon chip. The disadvantage of these is the size and the cost. We can also use on-chip capacitors and inductors, and by that I mean on the silicon chip itself of the circuit. This is limited by the fact that these elements have relatively small values and they don't perform too well due to low Q. In many situations, this means that we would want to use distributed components comprising transmission lines. Let's now talk about the Bode-Fano criterion. This criterion gives an upper limit on our ability to match to an arbitrary load. For a given load, the Bode-Fano criterion states the following. And this will tell us that the bandwidth is limited by the Q and the maximum reflection coefficient that we're willing to tolerate. Figure 5.22 in Posar's book states the Bode-Fano criterion for 4 different specific instances of loads. And if we assume an ideal bandpass characteristic shown in the upper part of the figure, then we will have the following characteristic, that gamma magnitude is equal to gamma m in the bandwidth, but it's equal to 1 otherwise. And working through the math, we find that the fractional bandwidth has to be less than a certain value that's determined by the Q and the maximum allowable reflection coefficient. Delta F over F0 is the fractional bandwidth that can be achieved with any possible passive lossless matching network. Q is the Q of the load, and gamma m is the maximum allowable reflection coefficient. Keep in mind that this sets the limit. In practice, any actual matching network will not be able to exceed the limits imposed by the Bode-Fano criterion, and in many cases will fall far short of what this criterion predicts. Some observations regarding this criterion are: a perfect match can be achieved only at a finite number of frequencies, discrete frequency points. Secondly, high Q circuits are harder to match. Third, for a given load, we can increase the achievable bandwidth by tolerating greater mismatch or by introducing loss to DQ the load, to make the Q of the load effectively less. Some points to consider. A real matching network can only approach and never exceed the performance predicted by the Bode-Fano criterion. In many cases, they fall far short of what this criterion predicts. For a given load, one matching network may approach the Bode-Fano criterion better than other possible matching networks. Furthermore, it is generally not possible to know a priori which matching network topology will yield the result closest to the Bode-Fano performance limit. So sometimes we have to do some trial and error in order to determine which matching network to use. And that concludes this lecture. Thank you for your attention.